Okay, so in this video, I'm going to show you a couple of examples of how we can use those equations for molecular speed and kinetic energy to calculate average molecular speeds at a fixed temperature for light molecules and for heavier molecules. And so we should see that the heavy molecules move slower on average, right, than the lighter molecules. They should move faster. And we're going to rearrange our equations for speed and kinetic energy to solve for the values that we need. And we're going to use this to compare relative diffusion and effusion rates for some different types of molecules. All right, so let's get started. And by the way, I'm doing more examples in these videos than I would normally have time to do in class. So I'm hoping that you'll find them useful. Of course, you're always welcome to skip over the extra examples if you feel like you have a good handle on something, or if you want to just do the practice yourself in the homework assignments. So to start, let's set up our equations for average molecular speed. We're going to be calculating the average speed. Remember that we derived in the last video that because kinetic energy equals 1/2 of mass times velocity squared, or mass times speed squared, I should say, that the speed of an individual molecule is going to be the square root of 2 times its kinetic energy over its mass, where this is the mass of a single atom, or a single molecule, I should say. We can simplify this equation and solve it using not kinetic energy but temperature. So let's go ahead and do that. So we know that kinetic energy also equals 3/2 RT over NA. That comes from our kinetic molecular theory of gases. We didn't derive this equation, so we're just taking that for granted right now that that is true. And so we have the square root of 2 times 3/2 RT over NA, where NA is Avogadro's number, of course, divided by the mass of a single molecule. So this gives us that the average speed is equal to 3 RT over NA times the mass of a single molecule. And I need to put one correction in here. In the last video, I said the total mass is the molar mass divided by number of moles. That's true, but importantly, we want to look not at the total mass, but at the individual molecule's mass when we're talking about molecular speeds, which is going to be the total molar mass divided by Avogadro's number of molecules per mole. So that means that Mi times Na equals molar mass, so we can plug that back in here, and we get that molecular speed is simply 3RT, square root of 3RT over molar mass. So that's the equation that we can go ahead and use to calculate the molecular speeds. Now we should check that the units make sense here, right? And that we're using the correct units. So we've got on the top, so first of all, we're trying to solve for speed, so this should be in meters per second. We have on the top R, and if we want to do this in SI units, R would be in joules, and since I'm just doing a dimensional analysis, I'll leave that off. R would be in joules. A joule is a kilogram meters squared per second squared. Okay, so that's going to be on the top, and we're going to have that joules per mole Kelvin, and that's going to be taken times temperature in Kelvin, divided by molar mass. Well, if I have kilograms on the top, that's all SI units. I better use SI units on the bottom, so I better use kilograms per mole for my molar mass. And if I do all of that, my kilograms will cancel, my moles will cancel, my Kelvin will cancel, and I'll get meters squared per second squared. Take the square root of that. I get my units of meters per second. So the units will make sense as long as I use SI units for R, so joules per mole Kelvin, and I use SI units for my molar mass, which means kilograms per mole instead of grams per mole. It's very important to remember this to get our units to come out right. Okay, so let's go ahead and calculate this for helium, O2, and xenon. So we've got to find the molar mass to put into our equation. We know temperature is going to be 298 K for all of these. And we know R, so we just need the molar mass. So for helium, it's 4.0026 grams per mole. But remember, we said we need to make sure that this is in kilograms per mole. So 0.004026 kilograms per mole. And we don't often use kilograms per mole unless we're doing these kind of calculations. O2 is going to be 2 times 15.9994 or 31.9988 grams per mole. So that's 0.0319988 kilograms per mole. And then for xenon, we've got 131.293, so 0.131293 kilograms per mole. And I think I'm going to need to rearrange this actually to give myself enough space. So let's start with just helium. We've got U equals the square root of 3 times 8.3145 joules per mole Kelvin times 298 Kelvin divided by 0.004026 kilograms per mole. Even I am tempted always to just write down the molar mass in grams per mole, so be very careful when you're solving these kind of problems that you remember to do them in kilograms per mole, because otherwise your units of joules aren't going to cancel out. So that's going to get rid of, again, if this is kilograms meters squared per second squared, that's joules. Then that we're going to get rid of our kilograms, get rid of our moles, get rid of our Kelvin, and we're left meters per second squared. So we get square root of 185,708.3 meters squared per second squared. Really big number, but we're taking the square root. And that comes out to be 1363 meters per second, but we only have 3 sig figs because we had 298 K. So essentially 1360 meters per second for our helium. And then let's do this for the oxygen and the xenon quickly, and we can compare them. So oxygen, O2, has a mass of 31.999 AMU, or 0.031999 kilograms per mole. So my speed is going to be 3 times my 8.3145 joules per mole Kelvin. And I won't do the dimensional analysis again here because we've looked at it now a couple times already. We're just going to say, okay, if we're in SI units all the way through, we're going to get SI units at the end. We know that. We've checked it. 999 kilograms per mole. And that comes out to be 482 meters per second. And xenon has a mass of 131.293 AMU. So its speed is going to be 3 times our 8.3145 joules per mole Kelvin times 298 Kelvin divided by our 0.131293 kilograms per mole, molar mass, which comes out to be 238 meters per second. So let's check that this makes sense. We've got our lightest species helium going the fastest, our heaviest xenon going the slowest, and our medium one in the middle. So that does make sense. If we were to plot this out, we would see our heaviest, our xenon, let's do xenon in orange, having this really low molecular speed with its average right around that 238. So this is speed on the x-axis in meters per second. Our oxygen having an average speed of around what did we say, 482. There's our O2. And this is our xenon. And of course, our helium would be zipping around at very high speeds. So it would have a really high average. And this is not quite to scale, but it would be up around 1360 meters per second. Okay, so it gives us some relationship between molecular speeds and the masses of molecules. One other thing to keep in mind when we're talking about molecules is that they're moving very, very fast, but they undergo a lot of collisions. The distance between molecules before they collide we call the mean free path. And just to give you an example, and this has not quite the right number. So oxygen at 25 degrees Celsius and 1 atmosphere of pressure travels at about 482 meters per second. But at 1 atmosphere of pressure, there's so many molecules there that can only go 60 nanometers before it runs into another oxygen molecule. And the molecule itself, remember that the sizes of atoms and small molecules is on the order of angstroms, tens of angstroms. So this is about 60 angstroms or 60 nanometers across an O2 molecule. So it can only go about 10 molecule lengths before it runs into another one. That's not very far between molecular collisions. So because the molecules are colliding all the time, this is what allows, say, a molecule of perfume. If you open a bottle of perfume at the front of a room, it's hitting so many other molecules. That's what allows it to bounce around and make its way to the back of the room. But of course it can't, it's going very fast, but it can't travel in a straight line. It has to bounce back and forth between a bunch of molecules. And so that process of molecules moving through a room we call diffusion. And there's also another process whereby molecules leak out of small holes, and we call that process effusion. So the speeds of molecules allow us to compare their rates of diffusion and effusion, diffusion and effusion. So let's do that now. So what is diffusion exactly? It's when you have a large opening or a completely open container. The molecules can essentially move in all directions, so they can move forward and backward through the opening. And they're undergoing lots of collisions. So you have these molecules of different sorts running into other molecules as they're passing through this opening, as they're diffusing outward. And so as I just said, an example of diffusion would be, say, perfume wafting through a room as the molecules collide with each other and spread. So say you opened a bottle of perfume over here, here's the air around it, and the molecules of perfume are moving out into the room, and if you're over here, it takes a little bit of time before you smell it. Someone closer to the bottle is going to smell it first. Someone even further away is going to smell it after you, because those molecules have to make their way to your nose if you're going to smell them. Effusion, on the other hand, is when molecules move through a very small pinhole from a region of high concentration to a region of low concentration. Now, the concentration here is less important than the fact that the molecules are moving so fast through such a tiny hole that they undergo no collisions in perfect effusion as they pass through that hole. So it's not collision limited, it's limited by the size and shape of that hole and how often molecules can get to that hole. So an example of effusion would be helium atoms leaking out of a tiny hole in the wall of a balloon. And in fact, balloons are actually at the microscopic level quite porous. They hold the gas molecules in because the holes are so tiny that the spaces between the rubber molecules that make up the balloon, or whatever material the balloon is made of, they're so tiny compared to the size of the molecules, and the molecules have a pretty low probability of hitting one of these holes, but over time, some of the molecules are going to hit the holes in the balloon and they're going to leak out. And this is why balloons deflate over time. So speaking of balloons, let's say we have a balloon filled with hydrogen and oxygen. We're at fixed temperature and pressure. Which molecule is going to leak out faster and why? So this is another question where you need to not only know the right answer, but have the right reasoning behind it. So pause this video, take a moment, think about this, and try to answer this question accurately. And I will come back in just a moment and explain to you what the thought process is here. Okay, so it is true that oxygen, O2, has more mass. It's true that O2 has a larger volume. So those two things are true. However, we need to answer why, which one leaks out faster and why. Okay, so the molecule that's going to leak out faster is going to leak out faster because it hits the walls of the container more often. So if we're at a fixed temperature, that means it's the molecule that moves faster. Leaks out faster is the one that moves faster. So we want to look at which one has the higher speed. Okay, so more moves faster means more collisions. We just calculated the speeds for O2 and H2, and we said that H2 has a faster speed, not because it has a smaller volume, but because it has less mass. So the most accurate answer here is C. H2 leaks out faster because it's less massive. And because it's less massive, it moves faster, has more collisions. That's why it leaks out faster. The qualitative understanding of that is probably the most important, the discussion we just went through. But we can actually compare the numbers, the rates of diffusion and effusion. Now, they're slightly different processes. Diffusion is a little more complex because it has to do with collisions with other molecules, but you can approximate them as having the same rate. So we can say the rate of diffusion and effusion go in the same direction. So if something diffuses faster, it also effuses faster. The law, the observational law that allows us to compare rates of effusion and diffusion is called Graham's law. So again, it's just a series of observations made about the way molecules behave. And what it says is that the effusion rate is proportional to the molecular speed, and therefore inversely proportional to the molecular mass, because faster speed equals more collisions with the walls of the container. Same thing that we just said. So the effusion rate is equal to square root of 1 over the molar mass. That comes from that equation for molecular speed. And so just like we compared for the oxygen and the helium, the relative rates of diffusion or effusion are going to be inversely proportional to their masses. So if O2 is heavier, it's going to move slower. So this rate 1, the rate of effusion of, say, the H2 is going to be higher, right? So if you have a big number on the top, small number on the bottom, that makes the number on the top over here bigger. So a small mass here means a fast rate over here. Okay, so you can compare the relative rates of diffusion and effusion by comparing the masses of the molecules. Okay, so how much faster would H2 effuse than O2? Well, we just need to look at their actual masses. You can say the rate of H2 effusing over the rate of O2 effusing. And I actually realize this can be an equal sign because we've now just got a ratio over here, equals the mass of O2, so there's our M2 on the top, over the mass of H2, which is about 2 AMU. We don't care about units here because we're taking a ratio, so the units are going to cancel out. Just put A's and cancel them out. So the square root of 16, or 4 times faster. So the H2 effuses 4 times faster than the O2, based on Graham's law.